But can I get rid of this? Yes, I know it's here. No, I don't want to hear anything. You just want this to go away.
This should disappear
Uh,
soon.
Oh yeah, it will roll out.
go away. Okay, now, yes, it works. So let's start. So let's do factoring. I'm going to try doing here so it has to take the chance to record me. Okay, so welcome to my talk today. It's called The Compiler is Smarter Than You, and that's why it can't optimize your code. I used to call it just that's why it can't help you, but this is a bit more accurate. And yes, this is a bit of a clickbait, but it's actually a bit more accurate than you would think. You know, like, so what do I actually mean? And what we will see in this talk. So we will be talking about some cases that I collected at my work, where the compiler missed some very obvious optimization. And we will talk about why they aren't actually obvious, and they aren't even legal for the compiler to make them. So we will then follow with getting the optimization to happen, to get the output of the compiler to where we want it to be, which is, you know, fast performant code. Mostly this will be vectorization for us. But since we are talking about optimization in C++, we have to start with the as-if rule, you know, and it says in a lot of standardized texts, but this is the main core idea, is that if you run a well-formed code, well-formed is important precondition. If your code is not well-formed, no further preconditions apply. Then the program will produce observable behavior. Again, observable behavior is a technical term from the standard. And then as if, this is where the name comes from, it was executed on the C++ abstract machine. Right? The C++ standard defines this abstract machine, which defines how C++ behaves. And basically, if we write correct code, it must behave as if it was executing on the abstract machine, not on the actual physical machine. Now, there are three exceptions to this rule. The first one is that there is copy elision, right? Copies, moves, destructors of the temporaries that are elided, none of these have to be compiled into the final executable, even if they have side effects. In fact, since C++ 17, I think, we have guaranteed copy elision, where the compiler is actually not allowed to make the copy and or move happen. It must skip them. Then there is new expression elision. The compiler is allowed to just not allocate memory through new. Even if the user has overloaded new and expects some observable side effect, it's allowed to just say no. I don't have to call it.
Are you sure about this? Because
yes.
First,
I'm extremely sure about this.
I have heard this kind of this.
Clang does this optimization.
I have observed this optimization, but I never know to do that actually using operator new, that overloading operator new will not prevent this.
Yes, it's even if you have side effects in your user provided operator new, it can just say no. I don't care.
Okay, because while I was working in pure storage of generalities and their stupid custom allocator, which was implementing using by overriding operator new. So I was thinking like, okay, so now we cannot use new expression elision because it doesn't use malloc, it uses some bullshit that is actually slower and doesn't put it on.
Yes, but
So you are saying that its replacement usually with alloca actually doesn't have the issue. So it's will optimize.
yes, like you can, this is of course like red optimization, right? It's hard to prove that you can make this optimization basically safely enough within the rules for this exception, but it is a rule that yes, you do not have to have the compiler is allowed to not have the side effects from your new because it doesn't call it. For example, it can see that like you are allocating just single int for some reason, and you are deallocating at the end of the function, and it doesn't escape, it can just say, no, this int goes on the stack, and that's it.
If you
And
just, there is much simpler example and much more common. You create a string and you assign there some 20-character string. And then you do something with the string and discard it at the end.
Yeah.
This is a pretty common use case and can apply.
Anyway.
Also, stud function is something that commonly gets hit by this optimization.
Anyway, there is third exception, which is about intermediate floating point exceptions. This is very obscure stuff. And since none of these three are actually relevant to this talk, they are only for completeness, then I am not going to explain this further. Like floating point exceptions, the compiler is allowed to do some magic with them. And yeah, none of these will be actually relevant to the talk. And yeah, keep this as a rule in the mind during the talk, because we are talking about optimizations, and all optimizations in C++ are guarded by this roof. So for our tests that we will see later, we have simple configuration. We will always compile with O3, target Broadwell for AVX2 instructions, and some other goodies, like count, pop count, and so on.
Experience and is better than Broadwell.
Anyway, we will be using DCC14, Planck 20. This is so we will see like what the two main compilers will do. Yes, there is also MSVC, but MSVC is not a real C++ compiler. It can hurt you, but it's not a real compiler, And so we will start with something pretty simple. We just want to call sqrtf in a loop. We have a lot of numbers. We want to take their square roots, and we will do it in a loop, and we want to do it fast, right? We have code like this. Just span of data. For every float, we want to replace it with a square root. Simple enough, right? So what do we want to see in the assembly? When we look at what the compiler will do. We want to see this instruction, sqrtps. This is amazing name, x86 assembly is great. And it processes 8 floats at a time, because this is the AVX2 sized instruction, encoding of the instruction. So, it has 256 bits in register, which is 8 floats. This is what we want to see. So what we will actually see, you see a lot of stuff in the function, but I will go through the important part of it. So first, we can see that actually GCC, always on the left, calls sqrtf. So already we see that it doesn't go for the hardware instruction, it goes in the function. But we also see that it does use the hardware instruction, right? So what's going on here? Well, let's take a look. We start by zeroing out our register we were using. Sure, we load float from this pointer. This is what we get into the function. Then we compare it. And if what we loaded is smaller than this, which is 0, because we just zeroed it out, we jump to L8, and L8 does some moves and calls sqrtf. So, and what happens if it's not smaller than 0? We use the have instruction, and then we just at 4, which is the size of the float, we load next, and we keep going, and we see if we are done with the loop, and if not, we go back again, right? And we see exactly the same pattern on the Planck side, with just some small changes. It's there again, right? Compare with the 0, call sqrtf, except it's switched around and so on. So what is happening here? So we see, again, we call sqrtf. If what we loaded is less than 0, what's square root of less than 0? It's an error, right? So the compiler knows that if you want, if you pass less than 0 to sqrtf, it is supposed to set the math r0, the r0 global variable that tells the user, oh, you did something wrong. So all of this is so that the compiler either takes the square root if it can, if it's valid, true for input, Or, it calls sqrtf to set the R0 for user as it has to. Again, it can vectorize the code because it would not be valid if you somehow gave it negative number to take the square root of. So the question is obvious. What if we know that inputs are valid? We have made sure that all the inputs are valid, and now we want to have the compiler, vectorize this simple loop and give us good performance. Well, we can use C++23, which has assume expression, and it tells the compiler this is true on the plane of undefined behavior. You just know the program promises that this is true. And you use it like this. I say that, okay, for every float, I'm going to assume that it's more or equal to 0. That there is no error case here to handle. So let's take a look at what the compilers do now that we told them. GCC, that's exactly the same code. But let's talk client instead.
Can you go back how you use assume? Never saw that the previous slide.
Yes, it's an empty statement. It's a C++ attribute, so double square brackets, and then you say this expression is true, and there are some limitations on how long it is valid, basically, and that goes very technical. But like for this, we just tell the compiler, yes, here it's valid until something else or opaque function touches this memory location. So GCC still the same, no change. But Clang is good. Clang goes okay. No error case to take care of anymore. I am not only going to vectorize this, I'm going to unroll it. So we are now processing what it was.
Sorry,
32?
stupid question. VSQRT-PS,
Yes.
And the other one is VSQRT-SS.
Yes.
SS,
Single and parallel, if is a good mnemotechnic. Yeah, I did not make this up. Blame Intel. But yeah, we have now not only vectorized the loop, we are doing it unrolled as well. And then there is like a bunch of more assembly for smaller loops and to catch loops that are smaller than 32 completely and so on. Okay, so what happened to GCC? GCC just ignores assume. It does not understand that this is a thing it can use, but it does understand built-in unreachables. This is basically a little magic function that says, if you get here, that's an error. You can't get here by definition.
Can you use unreachable to get this in a platform independent way?
Can I use unreachable? Probably yes, actually, but I would have to check whether it works or not with GCC. Anyway, so you use it like this. You say, if the float is more than 0, the error case, then unreachable. Or in other words, this cannot happen again, except we have to invert the condition. Let's take a look at GCC again, and it's already better. It no longer has the error case, right? There's no more calling sqrtf to set the R0, but it still processes the elements of the loop one at a time. And client still understands assumptions, built-in unreachable. It still does this. So how do we fix it? How do we get GCC to vectorize this code? So the answer is actually funny. You can start by updating to GCC 15, as I found out when I was double-checking these examples. Right? I found this last year. We had no GCC 15 back then, only 14. And GCC 14, for whatever reason, cannot handle assumptions in a loop. So it will never vectorize loop that has assumptions, even if it knows that without this assumption it would do it, and the assumption doesn't change anything. The moment it sees assumptions in a loop, it turns out vectorizer. But GCC 15 can handle this. Or you can go fast math, which actually never ever do this. But this is fine. Just say no R0 on math. I have never ever in my life used R0 from math. So this is, for me, this was basically free, and it gets GCC 14 to actually give you good assembly again. It doesn't unroll the loop, but it does the vectorization, which is the main thing that we want to happen. So, okay, this was the easy one. Let's go for harder stuff. What if I want a max element from a span? You know, I have a huge array and I want to find the maximal element. This will be easy, but it's actually harder. Again, we have a function that looks something like this. We have a span of a lot of floats. We take the lowest possible float, and then for every float in the input, hey, is it bigger than what we have? If yes, keep it. It sounds really easy. And you know what we would like to see here is Vmax PS. You know, just like floats 8 at a time, get the maximum of them. And what we will actually get. Well, of course, we won't get this right now. I wouldn't use it as an example if we did. What we get is just one by one, we will compare all the floats using Vmax SS, and then pick the last one. Clank, same stuff. There are just like some details in how they decide to basically organize the function, when do they check for empty input and so on. So, what's the issue? Vmax PS has semantics like defined by Intel what it does that are actually different than from this. So you can't use Vmax PS to implement this loop because then the behavior would be different. And this would be observable by the user because the user could get different element back between using Vmax PS and this. And the difference is in two places. First, Vmax PS has different behavior for nonce than this loop. So if you have not the numbers, that's an issue. And the other is signed and sign zeros, plus minus 0. Like these are somehow always terrible. Because to go into a bit more details, Vmax PS, if it has to compare two zeros, either a positive or negative, doesn't matter, it will always return the one on the right. You know, you can imagine it like doing 8 pairwise comparisons. This loop, if you run into a bunch of zeros, this will return the first one, not the last one. So that's different. And again, user could observe it because he would end up with different signs of the zero that he gets. So what do we do about this? We say, hey, compiler, we actually don't care about nonce, finite math only. Be careful with this. This is something we probably don't want to do, right? And you can say, actually, like, I don't care about signs on zeros either. Like, I want to point out, I don't actually recommend having either of these in your class. I'm just pointing out, you can do this, you can get that like this. So what happens if we tell this to the compiler? Yep, this is what we want. We will always just load a lot of new floats and compare them. Same for Clang, except again, Clang just goes, yep, I'm going to unroll this loop a lot. Clang really likes unrolling loops. So what if we don't want to change the global floating point behavior? So I haven't been able to convince either of these two compilers to do this. Technically, we have the tools in the standard to get there, right? We should be able to have them assume, we should be able to get them to assume that there are no nonce. And with some trickery, like with floating point operations, we should be able to explain to them that signed zeros don't matter to us either. But currently, none of the compilers actually can reason through it sufficiently to do this. Yes.
Can you change those settings locally with some pragma for each compiler?
Yes, you can probably change them locally with some pragma. But again, you are like basically changing for the floating point behavior to some region of code. And what if we don't want to? Not necessarily.
Did you make it work? Because I remember trying that and it just didn't work because GCC refused to accept the arguments in pragmas.
Oh, actually, I haven't tried that. Like you should be able to do it, but I haven't tried using pragmas to change it locally.
You might hypothetically just separate it as a separate compilation unit.
Yeah.
And as long as, like, I assume that you would not want to mix code with different kind of assumptions together. So if you could just separate this whole computation into a separate module, that would be like.
Yeah, you can. Yeah, you can basically, if pragmas don't work for you, you can do like simple CPP file with the function and change that one. But what if we actually, I can get rid of the no sign zeros for GCC only. Clang doesn't actually like get that yet. So what do? Is you use this little function called stdfmax. And it actually has behavior that's very similar to the hardware instruction, because what it does is that it says, if one of the argument is none, then I return the other one. This is like the big difference, this is one of the big difference with the Vmax and the plain comparison. And the other thing that it says is that when it sees a zero, when it sees two zeros to compare, it doesn't promise you what it actually returns. It just returns whatever. Like, it's specified that implementations can specify what they do. And when you do this, when you change your comparison to use stdfmax, you no longer need sign zeros for GCC. Yeah, Clang doesn't actually see this, and like technically you should be able to also use this to eliminate the issue with nums. Not quite. This is where the compiler do get stupid. So both are hard. How about we do something else? Yes.
Does it work when you split the arguments positions?
I actually don't know. Maybe I should add it, but it shouldn't, because like the way that the function is specified, it should do the same thing basically. So floats are hard. Let's try something simpler. Let's talk about integers. Those are nice and easy, and I want to talk a little bit about having integer comparisons, and we want to combine them. Basically, consider this. I mean, it's more of a C function, not C++, but I found this in the C code, so I keep it like this. We have this struct that has two integers inside, 2-byte integers, and we say this is like equality. We want to say if the first integer is equal and the second integer is equal, they are equal. Like this should be easy. And what we want here is simple. We want to load 4 bytes at the time, and then we want to compare 4 bytes. Because yeah, sure, like we can just load this and this at the same time, and they both have to be equal anyway, right? Let's take a look at what the compilers tell us. So first, GCC, it says no. Specifically, it does 2-byte compare here, and if this 2-byte compare is equal, then it jumps here and it does the other 2-byte compare. So GCC says no, I have to do both separately, and I have to add a jump in between. So what about Clang? Clang is usually the smarter one, and Clang says I have to do a comparison. It decides to jump if not equal, and then it does the other 2-byte comparison here. If you are not too familiar with like the explicit assembly, this is a 2-byte register. And this word PTR means load 2 bytes and so on. So yeah, by the way, aside from this, I think it's interesting that actually like Clang and GCC optimize the code for different cases. Like GCC says, I am going to optimize for the case where they are not equal. Clang is optimized if they are equal, and is specified if they are not equal. Anyway, so why can't we shoot the while loop? Why isn't it something that we can just blindly do? Consider this code. We still have the pair, we still have the same equal, and now we do something really stupid. We say, okay, I have 2 pairs, and I'm going to initialize only the first part, and I'm going to initialize it with different values. Then I'm going to call the equality function. As written, this is valid because we have set the a's to different values. Then these never have to be read. So the fact that they are uninitialized doesn't matter, right? because if it was just blindly read, then it would be an undefined behavior because you would be reading from an initialized memory, which we can do. But since we have made these different, we will never get here. So this is valid code, and the compiler has to keep it valid. If you want like some less stupid example of why this can be something that we want to happen, is that if you, for example, happen to have, if you like have a something bigger than just, like single AV, you can find yourself spanning page boundaries. And like you might not want to just blindly go across page boundaries because, for example, the user, the programmer, might know that like the other memory page is unmapped, which would be a hard error. But he also made sure that these are different, so you will never get it there. Yeah, so what do we want the compiler to just use the white load anyway, because our code isn't so stupid to do like this? How do we get there? So the s.r.o rule, we were talking about a well-formed program. And the compiler has to keep the well-formed program well-formed. But it doesn't have to do anything about ill-formed code. So, if it's ill-formed for pair B to be unreadable, then the compiler is allowed to always load pair B, because it won't break your code further. Like basically, if we invoke the undefined behavior ourselves as the programmers, the compiler does not have to avoid it anymore. This is just like full galaxy brain optimization. So what does this mean in practice? It's simple. We say, hey, equality takes the pairs by value. I mean, it's a 4-byte struct, right? Passing by value is literally smaller than passing the pointers. And now, if you call equality with pair that's partially unreadable, this is already undefined behavior. It's undefined behavior just to call equality if some like part of the pair can be read. Because when the pair was copied into the argument, you already had to touch the memory. This is like full galaxy brain reasoning, but it's true. So what do we get? So what do we get now? GCC is very conservative, doesn't agree. But Clang goes, yep. We just compared the two registers that you had to pass us to enter the function, set the result, we are done, we can go home. Let's talk.
Sorry, I'm not sure I'm following, but that useless, right? Because you had so the compiler was able to do the smart thing on code that doesn't work.
No, it works.
Yeah.
Like
we are still under the assumption that you have the second pair is uninitialized.
No.
No?
No, sorry.
Yeah, here I remember I was remembering this. So you moved away from that. Okay.
Yes. This is example of why the compiler can't do it on its own.
All right.
But if we as programmers know that we don't do something this stupid.
Okay, so pass by value, and so okay, got it.
Yeah, basically we say, hey, we will not do this. We will not do something this terrible.
I promise. Yes.
Yes.
And you promise by the signature of the function, which
exactly. So we pass by value. Now if we just make like partially initialized pair, it's now UB. But the compiler now can just go, yep, I can just load 4 bytes, compare 4 bytes, get going home. So how about alternatives? How about, or other way, like, yeah, similar like thing we can do, just say we will always read B, and then under the same logic, we should still get optimized result. We can do this, you can do this, you can just say, actually, we don't want short-circuiting AND, we will not be doing logical AND, we will be doing with binary AND. And this works on rules, right? This will get the same result. So, and this will improve the GCC assembly slightly. It will still do those two comparisons, but it no longer actually jumps inside. So now it understands that it doesn't have to jump away. It just doesn't. It just still doesn't see that you can just load it all in a single go. Clang, still smart, still loads double word, compare double word. still fine with everything. But I'm using GCC in production. So how do I get GCC to actually optimize this? We stop being subtle. We no longer play with like these tiny rules. You just say, okay, just read the goddamn memory and compare it. Right? We just say, okay, compare 4 bytes of memory. And if it's 0, then that's true. This means they are equal. GCC, and this is actually a problem. Like, this is not something I want to write in my code. Because if at any point I change the structure and now there is padding or something, instant bug, right? Because comparing the padding, those bytes are not specified how they work. So like they might be different, even though the pairs is the same. So this is error prone in the future, but it works.
Just do a static assert that it's 4.
Yes, this is possible. You can static assert that there is no padding. Basically, there is some new trait for this in C++ 26, I believe.
Yes, I think I don't remember what was that.
Whatever. So yeah, now we get the right assembly from GCC. Clank is still happy with us. This is good. And yeah, I want to point out one further thing about this. So the as-if rule talks about the original C++ code that the programmer provided to the compiler. This means that it can use the code before inlining to optimize after inlining happens. All right? What do I mean? Imagine that you have still this equality comparison that takes by value, and then you have this function foo that takes takes these by pointer, right? And the reference is the pointer is called into equality. Now, no compiler will not inline this. Every compiler with enabled optimization levels will inline this simple function here. But what's cool is that it will inline it still under the assumption that you made a copy. So by inlining it here, you don't lose the optimization. So as long as your equality-based function works properly, after inlining, you still get what you want from the optimization. And let's go back to C++ for a second. Let's stop writing C code. Let's do C++. Okay, now we have 10 bool operator per default, and this is just equality operator. We have the compiler do this. There's actually one slightly interesting thing about this. In that Clank is still correct. Like Clank is actually surprisingly good at this. But GCC here now removes the jump. It now understands that it doesn't need to jump away, even though when we had this C code, when we had just this function bool equality, it still did the jump. When it's default generated operator, there is no longer jump, but it still does the two byte compares and stuff. It got better, not nearly as better as it should. And yeah, we are getting to the end. Some conclusion to this. Compilers really like their language rules minutiae. They really go through every rule and just go, yes, this is correct. No, this is not correct. This is obscure as hell, but the language says this. So when you see some missing optimization, it's not always the compiler defect or the optimizer defect. Sometimes it's just a rule that you just don't know. I actually learned a lot from figuring out these. And of course, you can give extra information to help the compiler out. Yeah, I learned a lot from this. And one idea is that if you have doubts about whether the optimization is missing or whether this is something deeper in the rules, you can compare more compilers. What do they do? And if they give you basically the same thing, then you know that there is a reason for this. Yeah, that's the end. And do you have any questions? Yes.
You say we should not use fast math.
Yes.
Why?
Because fast math has two issues, right? One is that it breaks IDE. So if you depend on IDE behavior somewhere, you can no longer depend on it. The other issue is that it enables a lot of the optimizations. And the chances are you don't need all of them. You should basically do targeted targeted decisions, right? If you don't need the math functions to set r0, which I am serious, I have never ever like checked r0 after the math function, then you can say no math r0, and you will get this bit of performance without breaking every other like floating point code that you use. So like fast math is good to like put it into compiler explorer and see if it helps the compiler do what you want. But then, you should delete it and start using the individual settings to pick out the one that actually does what you need. And it also like tells you when you find like the settings that like do what you want, it also tells you basically where you should look for an explanation of why the transformation that you want to do isn't usually correct. And this then helps you to be like, oh, I don't care about nonce, like I don't care about preservation of their order. Or you can be like, oh, okay, this is actually like a big change to the code, and I don't want to do that.
Great.
Does fast math still affect the global?
No, fast math no longer builds in a global constructor to your libraries since either GCC 14 or 15. It's actually a very recent change because if you have used for fast math GCC in the last, I don't know, 15 years, maybe more, then it built in a global constructor into your object that would change the settings of floating point for your entire process upon startup. So then this is viral, right? So you would be like writing something where you actually care about your floating point math, but then you use some user interface toolkit, because like I don't care for drawing everything myself. I'm going to use Qt. Qt linked in a different library. And somebody compiled a library with OFast, which implies fast math, which builds in this constructor. So when you link against it, suddenly the behavior of floating point operations in your process has changed. That was amazing decision. Okay, anything else?
So this I'm asking only because you mentioned at the beginning about MSVC. I also don't use it, but I'm curious why I don't use it, but I expect it to be conformant to respect the standard. Like I don't know, maybe. So why it's not interesting for
It has a tag to switch to conformant to standard conformant.
Yeah, but it doesn't conform anyway. Right? Okay, so like on a philosophical level, none of the compilers are actually conformant. Like the language is so complex that we standardize bugs that the compiler can't even fulfill. But on a practical level, basically conformance types are like Planck, TCC, MSVC. And MSVC is also bad at most optimizations. So it's like you can look at what it does, but there is a good chance that it will just always do the wrong thing. Like, no, sorry, not the wrong thing. It will never do the smart thing.
But Harry Sutter, the C++ guy, used to work at Microsoft. I would expect he was the compiler team. So I'm discovering this now that it doesn't have a high reputation in the compiler landscape. I thought it was,
No, so this is like a lot of inside stuff, but like the basic idea of MSVC, the basic idea of Microsoft, like as a company, is backwards compatibility.
Yeah.
And so like MSVC has to be backwards compatible. And for example, so if they go and like improve their conformance to the standard, but now they break some code snippet from the Windows team, they have to roll back because the Windows team is much more like the backwards compatibility on the Windows team side is much more important than like any improvement to MSVC. Like there is a lot of politics and there is like a lot of stuff. Like MSVC, like once upon a time, I don't know, maybe 6-8 years ago, MSVC Microsoft was basically rebuilding MSVC backend with a like separate team with the idea that basically they would separately like get to something reasonable because the internals of the MSVC was a mess, and then just lift the new engine and retrofit, like splat it into the front end that they had. And they, as far as I know, they were pretty far along, like close enough to actually doing the replacement. But then politics happened, the team ended, and then this code, like this new compiler, has big rotted for a few years before it was restarted. But this time, to avoid, like, you know, this idea that you pay a lot of money into it and then it moves nowhere, it was restarted as the idea, like cherry picking the changes from the separate one into the current compiler, which is of course much harder because you can't just cherry pick your people analysis from different compiler because it depends on like completely different everything, right? And it has been moving very slowly. And like they promise a lot of movement on some stuff like modules. I'm not going to go into modules. Yeah, anything else?
When you said about MSVC and the difference from the integrating is in the C++ community working with somewhere.
No, it's every now and then, like C++ community actually deprecates something and removes it. You know, once in 20 years, but it still happens. Okay, no, I want to give an example of like MSVC issues, like the symptoms that you see from outside. Do you know the attribute for no unique address?
Oh no.
So there is an attribute, no unique address, that's like compiler hint saying, hey, this is a zero-sized object and I don't need to take its address. So it doesn't need to take up any memory. Right? This allows you, if you have like empty no, it's not the allocator, but like if you have unique pointer, right, it supports custom deleters. And it's promised that if the deleter is empty, it doesn't need its own state, then the unique pointer is only the size of normal pointer. But if it's not empty, then you need to store like the deleter inside the unique pointer and it's bigger. And one way to implement this is terrible metaprogramming, like absolutely terrible. And the other is to put them into the object and just say no unique address on the deleter. That's the intention behind it. And MSVC decided that to like claim full conformance, they are going to accept the attribute, and it will have absolutely no effect. So you can't use no unique address on MSVC to get the optimization. What do you have to do? Because they needed like the extra time to implement it, is use attribute MSVC namespace, no unique address. And it's just like, no. And they will never, ever change this. Because it would change ABI, and they don't break ABI anymore. So
yeah, but they have this kind of like called F permissive, and it basically disables the permissive mode, which basically chooses the behavior of a lot of things to be more conformant with the standard.
yes.
Oh, it's permissive minus. Yeah.
Yes, permissive minus, like disable. Yes, it fixes a bunch of stuff, but doesn't really change everything. For example, like last month, I got an update on seven-year-old ticket I had against MSVC that, hey, we have fixed this and released this, right? And it's an issue in that they do not properly handle hex escapes inside Unicode strings. Right? The proper handling is that if you have an hex escape inside a Unicode string, like U8 or U16 or whatever, then it is supposed to take the number in the hex escape and interpret it as a code point. That's how it's supposed to work. And they have implemented this. But for a reason that nobody understands outside of Microsoft, this behavior is not in permissive minus. It's in /ZC, something like UTF-8 char escape or whatever. And it's not in the permissive minus mode because, I don't know, like Microsoft. Yeah, but I think like if he wants to complain about compilers and stuff, we can move to a pub close by because we will be here a long time. Anything else for the talk?
Oh, wait. Oh, no.
No? Any other questions for the talk? Like,
Yeah,
no? Then I think.
Yeah, actually, I had one remark. that I was doing some stuff with SIMD, and I noticed that functions were not getting inlined for no apparent reason. And it got to the point that I realized that, well, I really think this function should be inlined. So I started putting this, I don't know how is it exactly called. I just decided to create a macro called force inline so that I could redefine it according to compiler. And in the end, I improved performance by almost 30%. Just by telling it to start finally inlining.
Yeah, like, yeah. And
And
inlining is the single most optimization in C++ in
yeah, but
practice.
I was surprised that it ended up compiling the function into like 6 instructions and it didn't inline it. And it was like the innermost loop.
Isn't it because when you use the CB stuff with the API, it has to pass it as a reference and not by value, so you cannot inline it or something like this.
Well, no, I thought to like for inline was forced, it just worked.
Okay.
And also, I did write the pass by value code, but like, yeah, it's just a variable that has some size and it's what was needlessly copied into the function. Well, there was no copy cost, no user-defined copy constructor or anything. I was just copying them.
Okay. Yeah, that's
And I saw that it actually emitted just the instructions copy 16 bytes, copy 16 bytes, and just keep it basic. And like it didn't have any problems with any of them, just didn't inline for no apparent reason. But on the other hand, I have found that at some places, if I edit force inline, it did get slower.
yeah, we at work we have quite a lot of usages of Fortnite, and removing it totally did cut us back 4% speed improvement on rendering.
Oh, yeah, you need to like I have found these places by inspecting there is this tool called call grid.
Yeah.
And it can track you how many times a function is called, like exactly. Tells you how much time is estimated by the calls themselves, how much is done by the function. And it shows you the instructions of every functions you have. And this very clearly shows you that, like, yes, this looks like something that could be inline. It's very easy to find there, to find these candidates and play, yeah, find a few places in this force inline and you get a performance, but when you do it only when you should, because
Yeah, it's over abuse of power copies.
yeah, and it's like